So when constructing free body diagrams, there are 5 steps we do every time, and then this step 0 kind of depends on whether or not a drawing or an image has been included that we're constructing a free body diagram for. So step 0 is, if you need to, sketch the system and its surroundings. Then every single time, step 1 is to identify the system we're looking at. The way that you can communicate this is by enclosing the system with a system boundary. To do that, draw a dashed line around the object or objects that constitute the system. After you've identified the system and communicated that by enclosing the system within a system boundary, step 2 is to shrink that system to a point at the center of coordinate axes with one axis parallel to the direction of motion. Now, the reason why we do this is sometimes people do draw those force vectors directly on top of the image. However, I find that gets really messy and confusing to identify all of those forces. So we draw it off to the side with a dot that represents the entire system. And then attached to that dot are all of those interactions, those forces that we're trying to identify on a free body diagram. Now, after you've shrunk that system to that point, step 3 is to represent those relevant forces that act across the system boundary from step 1. And make sure that we label those force vectors. So that way we can communicate what is causing the force, acting on what, and when we know it, what type of force that is. Step 4 is to indicate which forces, if any, are equal in magnitude to other forces by scaling the vectors. Now, to do that, just draw those force vectors the same length as another force if they're supposed to be equivalent in magnitude. And then finally, the 5th step is to indicate the magnitude and direction of the sum of the forces acting on the system. To do this, write a summation equation or equations that explain whether the forces are balanced or unbalanced. And then this can be used to explain whether the velocity is constant or if there's accelerated motion. So we have 3 examples that we're going to be going through to construct free body diagrams that will make use of steps 1 through 5. So our first example is to draw a free body diagram for the skater moving at a constant speed across frictionless ice. So the first thing I'm going to do, seeing as this sketch has already been drawn for me, is to draw my system boundary. There we go. My system boundary is going to be the skater, because that's what we're drawing the free body diagram for. Step 2 is to shrink that system down to a dot. This dot is going to represent our skater. Then I'm going to identify what forces are acting on the object. Now, the first force that I will typically always be representing is the force of gravity. And that force is going to be pulling down on our system, pointing to the center of the Earth when we are on Earth. So that's going to be an arrow pointing down. This is going to be the force of the Earth acting on our skater. So E is for Earth, S is for skater. And the way I'm setting this up is I'm first identifying what is causing the interaction, that force, which is going to be the Earth, and then I'm identifying what is the second object in that 2-object interaction, which is a force. So this is the first thing that I'm going to be seeing. It is called a non-contact force because that is going to be one of those types of interactions that is exerting a pull or a push on an object, but it's not one that we can visually identify just by looking at our system boundary. But after this, we can just see what is physically touching the skater and what would be crossing that system boundary. Now, the skater is touching 2 things. It is touching the air, and it is touching the frictionless ice. Now, we don't really have any reason to believe that the air is exerting a force on the skater, so we're going to discount the interaction between the air and the skater. That would not be one of those relevant forces. However, this skater is interacting with the frictionless ice. So there will probably be a force that we need to include on our free body diagram. Now, the ice is underneath the skater, so it would be exerting a push upwards acting on the skater. So I'm drawing an upward arrow. F for force is going to be the ice acting on the skater. Now, I ended up scaling this, which is step 4, to show that the force of the ice acting on the skater and the force of the Earth acting on the skater are the same size. The reason why I'm saying that is I can see that this skater is moving at a constant speed. That means that the acceleration should be 0. Which means that all the forces acting on the skater are balanced. Because I cannot see any other interactions between the skater and anything, then that must mean that these are the only two forces we have here. So, step 5 is to identify the sum of the forces acting on the skater. Now I'm saying because it is a constant speed, there should be overall 0 newtons of force acting on the skater. We have 2 of these forces acting on them. That is going to be the force of the ice acting on the skater and the force of the earth acting on the skater. Because they're pointing in opposite directions, I assign opposite signs to those 2 forces. So the force exerted by the ice on the skater is completely balanced by the force of the earth acting on the skater. So if we were to sum those 2 up, it would add up to 0 newtons. So this would be a free body diagram, acting on a skater moving at a constant speed across frictionless ice. Our second free body diagram is going to be a force diagram, which is another term for a free body diagram, for a softball player who is slowing as she slides into the base. So slowing means that the velocity is not constant. So there's going to be some acceleration here. So our step 0 is already done for us. We already have that sketch of the system and its surroundings. So that means I'm just going to move on to step 1, which is to draw my system boundary. So I'm just going to be enclosing my person within this system boundary. Then I shrink it down into a single dot. The first interaction, that first force I like to draw, is the force of the earth acting on the object. Force of the earth acting on the softball player. So I'll just do E for earth, P for player. Now I know that the softball player is probably on the ground. So that's going to be the ground underneath them in relation to them. So that would be an upward force. So force of the ground acting on the player. Now, I am drawing these 2 forces, the same size, because I see no change in motion, up or down. This softball player is not accelerating up, they're not accelerating down. So the vertical forces here will be balanced. However, if she is moving to the right, she starts off with some velocity, and then as time goes on, her velocity is decreasing. That means that she's going to have some acceleration pointing to the left to slow her down at each of these increasing times. That means there needs to be some unbalanced force with that force pointing to the left. Now, besides the ground, the only thing touching her is the air. However, the air is probably not going to be exerting a sufficiently large force on her to be causing that acceleration to the left. So we can't see what else is touching her, which is the ground. While it is pushing up on her, it can also be pulling on her while she is sliding to the right. So we can have 2 interactions between the ground and the player by showing that this force vector is pointing to the left. This is the force of the ground acting on the player. Now, we have 2 of these interactions that are labeled the same, because the 2 objects that we have for that upward force and leftward force are both the ground and the player. So if we were to write a single summation equation, it might be confusing which one we're showing and which ones end up balancing out. But the way that we can rectify that is by writing 2 separate summation equations. We can write a summation equation for all of the forces that are horizontal, or acting along the x-axis. And then we can write a separate equation for the sum of all of the forces acting on the y-axis. That will allow us to explain the motion left and right, and up and down a little bit easier. Because for our vertical forces, overall, because we're not seeing any acceleration up or down, we know that those forces need to be balanced. So that's upward force of gravity, oh sorry, not gravity, the upward force of the ground on the player balances out the downward force of the earth acting on the player. That force would be the gravity. And then we're going to have for the sum of the force in the horizontal direction. Well, it is not going to be equal to 0 newtons because there's some acceleration to the left. And we can end up calculating what that lack of 0 newtons is going to be based on those forces along our horizontal plane. In that case, it's going to be the force of the ground acting on the player. And then that makes it a little bit easier for us to correspond it with our free body diagram here. Just writing two summation equations to talk about the vertical and horizontal motions of this object. That can explain the acceleration horizontally and the acceleration vertically. In this case, we only have a horizontal acceleration, whereas the acceleration vertically is 0. Now, our first example of the skater moving at a constant speed along frictionless ice was an example of a perfectly balanced free body diagram that just focused on two forces, which could be explained using a single summation equation. Our second example is unbalanced forces that explain an acceleration of a person. In this case, it was easier for us to identify the acceleration by writing two separate summation equations, one horizontal and one vertical. This third example will introduce another concept, which is going to be how we can focus on forces that are applied at an angle. So this free body diagram that we're drawing is for the sled and the kids. They're being pulled at a constant speed. So overall, we know the total sum of the forces needs to be 0 newtons. So when we draw our free body diagram for that, we need to make sure that we are going to be including the two kids and the sled, and then we need to identify the forces acting on that entire system and explain how all of those forces are going to be balanced. So I'm going to first shrink my system down to that single dot. I identify my downward force of the earth acting on the sled and the kids. Then other things that are touching it. Right now I'm given no indication that the air, which is definitely touching the sled and the kids, would be exerting a force, so I'll discount that. Then there's just going to be two things that are going to be touching the sled and the kids. The ground and the person pulling on that rope, that handle, or whatever that is. So we're going to first focus on the force exerted by the ground. So we're going to have an upward force of the ground acting on the sled and the kids. And then we're going to have, because the person's pulling up at an angle, an up and to the right force vector. That is going to be the force of the person on the sled and the kids. Now, just looking at this, it does not look like there's balance, because we have one force directly straight down, we have one force directly up, and then we have one force up and to the right. Now, we might be able to adjust the scale to explain how the two upward forces and the one downward force might be balanced to show 0 acceleration, but we need some force pointing to the left to balance out some of that pull to the right. So that's where we can talk about that other interaction the ground might have on the sled and the kids. That can be that frictional force, which would be another force of the ground acting on the sled and the kids. However, even if we leave it like this, it is not super clear exactly how that force of the ground acting on the sled and the kids balances out the force of the person on the sled and the kids. This is where we can break up that angled force into how much to the right it pulls and how much to the upward direction it pulls. Because not all of this force is applied pulling it to the right. Only some of it is. So if we treat that as like a leg of a triangle, this force in the horizontal direction would not be as long as that full up and to the right force, but it would be significant enough to cause some motion to the right that would eventually be balanced out by that force of friction to the left. And then we would also have an upward component, that vertical component of that person acting on the sled and the kids. Because overall, we know that for our summation equations, the horizontal one should be balanced, so 0 newtons overall. The force of the person acting on the sled and the kids does not fully explain all of that rightward force. So if we just focus on the x component of that, that could explain how it is balanced out by that force of the ground acting on the sled and the kids to overall be balanced horizontally. And for the vertical components, those two should be balanced because overall the sled is moving at a constant speed. So that means that those two upward forces, the force of the ground acting on the sled and the kids, and some amount of the force of the person acting on the sled and the kids, that vertical component, those two combined should balance out the pull of the earth acting on the sled and the kids. So for this third example, we're talking about how we can break up angled forces into horizontal and vertical components to more easily explain how forces overall can be balanced to produce a constant speed.